In this example, I want to show you how to set up a model that shows the effects of varying temperature on mixing in surface water. And what I have in mind is that here's a surface water body. This is Lake Hartwell behind campus. Um, we might also consider something like this, a wetland area where it's obviously much shallower here. And the idea then is that the temperature, that is the air temperature in the incoming radiation and convective heat transfer, it will vary with time. During the day, things will warm up, and then at night, they'll cool down. And so the question then is, to what extent does that temperature variation cause mixing of these water bodies? Does it happen at all? And if so, what are the characteristics of that mixing? And that would be important. For example, if you are living in this water, if you're interested in aquatic ecosystems, then the extent that mixing occurs will govern the exchange of dissolved oxygen and other compounds between the surface and whatever depth the mixing occurs. It'll also perhaps bring compounds that are down at depth up to the surface. And there are a variety of implications there. And so let's take a look at how to analyze this situation. And it'll be pretty simple. We'll just have a block that represents kind of a slice down through the water column here. And we'll apply a convective heat transfer to the surface, and it'll vary sinusoidally like this. And the idea is that that would be heating and cooling on a perhaps a daily cycle. We're going to look at it on a bit of a shorter cycle, but it'll be straightforward to vary the periodicity of this cycle and characterize the effects. Okay, so let's switch over to the analysis. So here's the geometry. It's just a square, 2/10 of a meter on a side. And the idea is that this will be the surface of the water, and this will just be an arbitrary boundary, though we're going to assume that it's a no-flow boundary. And the setup is, well, it's going to be the same variables that we used in the previous model. This step is no longer used. And the setup here for the physics is, let's see, these are going to all be defaults. This will be important though. The initial value of the temperature is 293. Now the default is 293.15, and for the convective cooling boundary condition here at the top, what I'm going to do is use that default 293.15, and then I'm going to apply to it this sinusoidal function. So temp f, actually I did add a few terms here in the variables, and one of them is this expression temp f, and it's the sine of pi times t divided by the period of the variation times the del t. And so the del t will be 1 degree, and for this example the period is going to be 1 hour. So this will show what happens if we raise the temperature by 1 degree and then drop it by 1 degree over 1 hour. And so let's see. Yeah, in this case, let me just explain while we're here. We're calculating the Rayleigh number, but in this case, the length of the thickness of the slab is a little bit unclear because, well, I'll show you about that in a second. We'll come back to this and I'll show you how we calculated the Rayleigh number. Okay, so let's go back to the physics setup. The initial value then is 293, and the boundary condition up here at the surface is going to be 293.15, and then this sinusoid. So this value here will be the average temperature, and the temperature then will vary with respect to this. This is going to be important because even though that's just a small temperature change, 0.15 degrees, it means that there'll be a body of water down here that'll be cooler than the average temperature up here. The volume force is the same as the previous analysis. And let me also point out under initial values here that I just set the initial pressure equal to 0. In the previous video, I gave you an expression for the pressure that, as it turns out, I realized after I made the video that that pressure in the video is off by a little bit. That's the pressure distribution for a layer that's 1 meter thick, but I've shortened it through the course of developing it, and so that pressure is off, and it doesn't really affect things too much. So I'm just going to start it off at a pressure of 0. Let's see, the pressure point constraint, that's the same as last time. And then one thing I did change from last time is this wall boundary condition. The upper surface here is it's a wall boundary condition, and I used a slip condition. And so what I have in mind is that's representing a free surface of the water. On the previous analysis, it was no slip, and that would be representing a layer of water that was sandwiched in between two walls. Okay, so that's the extent of the setup. The particles, it's pretty much the same as the previous video, except the locations of the initial particles are different. So we do the analysis, and this is the mesh that I used, and we go ahead and run the analysis. And with this mesh, this analysis on my computer takes about 4 minutes. So you might try running it on a coarser mesh and getting things worked out on the coarser mesh. One thing I found though is that at least when I was doing this, if I ran the flow and heat transport on a coarse mesh, that when I went and used that for the particle tracing, it was quite slow. And I'm not quite sure why this is, but it's probably because it has to interpolate what the velocity is, and the points were pretty far apart. So that seemed to take a good bit of time. So this finer mesh causes the flow and heat to run slower, but the particle tracing runs much faster. So I did the analysis, and here's what the flow and heat results are like. Let's take a look at the player here. I ran this previously, and let me see. Let me get this a little bit enlarged. And so here we go. So first of all, we're heating up the surface. That causes the upper part of the water to heat up, and we're running it for an hour period. Okay, so we're 1,000 seconds. 1800 will be the peak heating. So right now we've reached the peak heating, and now we're actually starting to cool. And the way I have the temperature contouring, you don't really see that, but now you do. And so here's the cool water being produced, and you can see the onset of convection and these Bernard cells. And there's the size of the Bernard cell, about equal to this thickness, which is the thickness here, right about that depth. That's the depth of the temperature anomaly. So it seems like what's happening is during heating, we have this temperature anomaly that penetrates down about 5 centimeters, and that forms the region that then is going to be active during the convection stage when cooling takes place. So this is 2 cycles, and here's the second cycle, and you can see these bodies of cool water coming down, and the heat is dissipating as the cool water spreads out. And then we reach the end of the simulation. Okay, so kind of a neat effect where as we heat it up, we've got stable heating. So this would be all during the day. It heats up. If you go out for a swim, well, at this scale, this would be if you go out in the summertime and swim in Lake Hartwell, what you find is that this heated layer is about a meter or so deep. If you're horizontal and swim horizontally, then you're in the warm water. If you're up vertical, then your feet are down in the cold water. This is a shorter heating pulse, and so it's a thinner region, but it's the same principle. While it's heating, it's stable. But then once cooling starts, and notice cooling starts right about here, and so we have to cool it for a while. Here we're at 2400 seconds, and then all of a sudden we have enough cooling to have a density contrast here, and the cool water sinks, and we get this characteristic downward flow, and then flaring out of the flow. So it goes down and it flares out in this this characteristic pattern. Sort of, it's got this kind of rounded head on it, and then forms the circulation cell down about this depth. That's exchanging heat by convection, and then the cycle begins again as we start to heat. Okay, so apparently what's happening here is that this heating cooling cycle causes a period of stable heating pretty much by conduction, and then during cooling it becomes unstable and mixes, and that cycle repeats itself. So I did some other plots. Actually, here's the surface heat flux, or the heat flux at several different depths. So I put in a cut line, and the cut line is here, and then I used line integration using that cut line, and this is the vertical flux. So I integrated the vertical flux across that line. So that's the kind of the total vertical heat flux, and I plot that as a function of time, and I do it for different depths. So right here at 0.19 meters, this is the height in the model. So if we take a look at the geometry, 0.19 is right up here, 0.15 is right here, and 0.1 is right here. And so we can see that we have a negative heat flux during heating, and then the positive heat flux, this is during cooling. This is just 1 centimeter below the water surface, and so we get this much higher heat flux during cooling because of the convection. And then the cycle repeats itself. We also get some oscillations here because of the convection. And if we go down 5 centimeters depth, this is the pattern. So very much muted, still getting some vertical convection, but not anywhere near as much as what we do at shallow depths. And then we go down to 1/10 of a meter, and there's a little bit of stuff going on, but it's pretty stable. So this kind of effect, where the surface is very active and it dies out with depth, it really shows up in the particle analysis. And if we take it back to the initial, here it is, and we can go, I think not surprisingly here, this is all during heating, and we essentially have no movement of the particles. So we get to 2400 seconds, we've been cooling it a bit, And then all of a sudden, between 2400 and 2700, we have the onset of convection and the mixing. You can see that there's downflow, upflow. So there's a Bernard cell, another one right here, another one right there, and that continues. And this goes on all while cooling is taking place, and then we start to heat. And let's see, the heating starts right, well, here's 3600, so the heating actually starts right about here. Um, and we still have the convection process going on, but right about now, you see that it's heated up again, and now it's stable. I can rock back and forth, and I don't really have any movement of the particles. And now um, and then we cool again, and we get motion. So this shows very nicely, I think, the net effect of these two heating cycles. We've got a zone that's between 0.14 and zero point 0.2, so 6 centimeters thick, pretty well mixed, and then below that, not much. And so that gives us an idea of what kind of mixing we would expect for this heat cycle. So this was just a 1 hour heat cycle. What'll happen is with a longer heat cycle, like a daily heat cycle, this will penetrate further. And then seasonal heat cycles will penetrate even further. And in many cases, seasonal heat cycles will cause the entire lake to turn over and mix.